should be working. I think that we are live. But as per usual, we will just give it a minute to get things set up. Let us know in the chat if you are there. We're keeping an eye on the YouTube chat. So if you're watching from a different streaming service, we might not see your messages. So come on over to YouTube if you'd like to talk to us throughout the stream. For those that haven't watched before, I'm Sophie, and this is Jamie, who's going to be joining me today, walking through some hypothesis testing for associations. We're really excited to get started. I think, select star from awesomeness. I like it. Yeah, that's what we're going for today. On this kind of, where I am, it's a little bit cloudy, and I don't know. I'm ready for some fun coding together. Cool. So it seems like people can see us, and we might as well get started because we've got a lot of material to get through today. I don't know how much of it we will actually get through. So with that, I will share my screen.
Sophie, you do have one question from the chat. Did you break Alex after last week?
No, I don't think I broke Alex. Alex could live stream all day long if somebody would allow him. But we wanted, oops, that is not what I meant to share. We wanted to mix it up a little bit. Jamie also very much enjoys live streaming. So, and he is also helping me with some of the master statistics phase 2 work right now. So, so yeah, we're all kind of running this live stream series together, me, Alex, and Jamie, and we're excited to have Jamie today.
I'm excited to be here.
Yeah, and Alex is in the chat confirming that I didn't break him. So, all right, let's get started. So this week, we're actually going to be returning to a data set that we used earlier in this series. So this is, I think it's the first data set we actually used. It's the heart disease data set. So as a quick reminder, this is a set of data for a sample of patients who were screened for heart disease. And some information about those patients was collected. And we're going to focus in on a smaller subset of that larger data set that we looked at in the first week. And so for this week, we're just going to look at a few of the variables, and we're going to see if we can try to understand the relationship between each of those variables and this heart disease variable, which indicates whether or not a patient was ultimately diagnosed with heart disease. I see some people from various places in the chat, and I see a question, what do you do when you don't work on data? I mean, I don't know. I feel like maybe there's two ways to interpret that question, but I feel like we're all just working on data all the time. Data is everywhere. Anyway, so basically similar questions to what we were looking at the last time Jamie was on. So I think the last time Jamie was on, we were talking, or actually maybe 2 times ago, we were talking about relationships between variables. And we looked at some plots, and we looked at some summary statistics like correlation or a difference in means. And in that case, we were looking at a data set and calculating summary statistics for that exact data set. But in this lesson, we're going to start talking about hypothesis testing for an association. And the reason why this is a little bit different is that in this example, we have this sample. Here, I'll actually run some of this code so that you can see. We can take a look at the info actually to see how many rows there are. right? So there's 303 patients in this data set. So we could look at this data set and understand the relationships between different variables. So we could understand, like, are there more males or females who are diagnosed with heart disease? Or do people who are diagnosed with heart disease in this data set tend to have higher cholesterol or something like that? For today, though, we're not interested in just this data set. We're actually going to be trying to think about how this data set can tell us something about heart disease more generally. So we're going to kind of open things up and say, like, based off of this data, we're going to imagine that this data is randomly sampled. So these people were randomly sampled from the general population. And we're going to say, based on this data, can we understand what predictors are, or what variables, what things about a person are most predictive of whether or not they're diagnosed with heart disease out in the world, not just in this data set. Cool. Great. So I see there's a question about what kind of data is this? This is, well, I'm going to answer that two ways. So this is a tabular data set in its format. So Jamie, do you want to discuss really quickly what tabular data is?
So yeah, tabular data is basically just data that is in table form, as we see here. So each column represents a variable in the data set. So we have age, sex, trust, BPS, call, just like a bunch of different columns. And then the values within the columns like are part of like each of these variables. So some of the variables in this data set are categorical and some of them are quantitative. So for example, I think like one of the columns that we're going to look at here is going to be I might pronounce this wrong. Thalach.
Yeah,
Thalach.
names are really bad. So I think this is Thal. So Thal refers to the heart, and then this is short for achieved, because it's related to like the heart rate that you achieve during an exercise test. Yeah, we'll go over the exact meaning. Yeah. But so, exactly. So the tabular data is just data that's arranged in rows and columns. And then kind of the next level down in terms of what kind of data this is it's being stored as a CSV file, which is just a common format for storing tabular data, but there's lots of other ones that we could read in. Cool. So I think let's get started. I'm gonna kind of walk through some examples of tests, and then even though this is not in the stats path, I think we're going to do some simulations of tests too, because I think it's fun and it helps us understand. So the first thing I want to do is let's take a look at some of the quantitative variables. So things like, and we'll go through what they all are. So we've got age, which is just the age of the person in years. T-rest BPS is, I believe, a blood pressure reading at rest. So BPS is blood pressure and T-rest is, I think blood pressure at rest. Call is cholesterol levels. We're going to ignore these two. I think if you joined in the first series or first session, you'll see these are actually categorical variables. And then we'll focus on Thal achieved, or heart rate that's achieved during an exercise test. And the way we'll do that, yeah.
Oh, sorry. We have another question that I think will be of interest to you in the chat. So someone asked, when inspecting associations at this level, can we talk about predicting, as in flagging which variable is predicting which?
Yeah, so I think it's really, I'm not sure if I fully understand the question. So if I don't ask, or if I don't answer it to the degree that you're hoping, then definitely let me know and I can try again. But I think it's interesting to actually think about the difference between looking at an association and figuring out whether you can use that association to make a prediction. And so if you see an association in the data, it doesn't necessarily mean that one thing causes another, and it doesn't tell you about why. It doesn't tell you anything about the why for that association. So one piece of complication is that if you really want to make any sort of inference about causality, like if you lower your cholesterol, you'll be less likely to be diagnosed with heart disease or something. That kind of research requires focus on the design of the experiment, not the actual analysis so much. I mean, the analysis piece too, but you can't really answer those causal questions with simple methods unless you have set up the experiment to do so. But then there's the next piece, which is that it's a different problem to try to like set up a predictive model, for example, of who's going to be diagnosed with heart disease based off these factors than it is to look at each individual variable separately. We definitely have some upcoming new content on predictive models, which I think will be hopefully useful to people. But yeah, we can definitely look at flagging, like thinking about which of these variables, for example, is most predictive of heart disease. So I'm going to the way I'm going to do this to start is I'm going to use that same like group by function that we used earlier on when we were talking about summary statistics. So what I'm going to do is I'm going to group my data set by heart disease, so whether or not someone has heart disease. And then I'm just going to calculate the mean of those, like by those groups for each of the quantitative variables. Cool. So looking at this, I don't know, Jamie, do you want to
Yes.
talk about any of this? Like, what do you see here?
Yes.
We can kind of ignore these two and focus on the other four.
So I guess I'll just like look for like mean differences across each of the columns. So I think the one that sticks out to me the most is, I still don't remember how I'm supposed to say it, the thalac, but I'll call it that. The one column on the far right. So there seems to be a pretty big mean difference when heart disease is absent versus present. So that might be like one I would want to analyze. And then also the cholesterol level column also seems to be a pretty big mean difference. Like when heart disease is present, there seems to be like when heart disease is present, like there's seems to be a higher average level of cholesterol. And then age and I think the resting blood pressure column, like there's also like a somewhat noticeable mean difference. So like those are all columns that we might want to analyze to see if there actually is truly a mean difference across these variables.
For sure. Yeah. So it looks like there's differences across the board, but as Jamie pointed out, some of them are definitely bigger than others. So we see like the biggest difference here. And we can also do this for median if we wanted. Here, I'll actually just grab this. It might look a little different. I'm not sure. I think, honestly, so interesting. So for median, it's the same median resting blood pressure for the two groups, even though it's slightly different here. So that's interesting.
That is really interesting.
Huh. And the median age difference is actually even larger than this. Interesting. Cool. I think beyond just looking at these pictures, it's useful to actually, or these tables, it's actually useful to look at a picture. So there's a few different options for pictures that we could look at, but I find that a box plot is really useful. So let's do that. Let's do it for, I think, what did I do in the final? I did thal achieved or thalac. I, of course, chose the most complicated sounding one. So let's do that. So we're going to do x equals heart dot thal. Oh, no. disease and y equals heart dot thal achieved. Let's see what that looks like. Right, so we see that difference even more clearly. We see that thal achieved is higher for people who have no heart disease or who are not diagnosed with heart disease. So basically people taking this exercise test, they can get their heart rate up higher if they don't have heart disease. If they do have heart disease, it seems like there's some sort of limit or lower limit to how high they can get their heart rate during this test. So that's interesting. So like I said before, I think the next question, and actually, I think let's pick one that is closer. Which one was close? T-rest BPS, maybe?
Yeah, it's pretty close. It had the same median, so.
Right. So let's see T-rest BPS. So here's one, right, where when we looked at the means, so let's scroll up for a second, looked at the means, it seems like blood pressure, resting blood pressure was slightly higher for people who were diagnosed with heart disease, like very, very slightly higher mean, not even a slightly higher median. And when we look at this box plot, we kind of see what that looks like. It seems like there's a larger range maybe for resting blood pressure among people with heart disease. But for the most part, right, like these boxes look pretty close together. And the question is this result, like if we found 100,000 more people and we collected their resting blood pressure and then we recorded whether or not they were diagnosed with heart disease down the line, if we did this for 100,000 more people or 1 million more people, would this picture still look like this? Would there still be a difference in the means? Would there not? Is this just a result of random chance? In the same way that we talked about the binomial test. And same thing here, right? Like it's possible that there's just a difference between these two groups because of the random sample that we chose. I don't know. What do you think, Jamie? Do you think that this big of a difference could be due to randomness?
I think less likely for like these two box plots. I also think it depends on like the size of the sample. So like
So
depending on like
303.
Yeah, with like 303 different data points, I think that there clearly is like it seems like there definitely is an association for the phthalac group, but for like the resting BPS, I feel like this one is like requires like more analysis to see like is there actually like some sort of something going on here between the resting blood pressure and like whether or not heart disease is present.
Yeah, totally. I tend to agree with you. So I think with that, let's jump into trying to simulate how we would run a hypothesis test here, because I actually think, I think two sample t-tests are probably the most commonly used hypothesis test, and a lot of people don't know how it works underneath the hood. So I think you all will be really benefited by hopefully seeing this at least once. So let's give it a try. First thing I want to think about is if we're running a hypothesis test, we have to start with a null and alternative hypothesis. So I'm going to switch to Markdown. We're going to write out our null and alternative hypotheses really quickly. So start with the null. Jamie, what do you think the null hypothesis test is going to be? So again, what we're trying to understand is whether this difference in group means is going to be true of the whole population. So like if we're trying to come up with standards in the USA or maybe global standards for what predicts heart disease or what is associated with heart disease. We want to know if this kind of a mean difference that we're seeing here is going to persist for that larger group. So thoughts on null hypothesis?
So I would say the null would be that there is no difference. So basically that there would be no mean difference in, are we doing that dialog here? There's no difference.
Or should we choose one that's a little bit easier? Let's actually look at, what did I do earlier today? Because I thought that was a good example. Let's do T-rest BPS. Let's do the resting blood pressure one.
Yeah, so if we're doing resting blood pressure, it would be that there's no difference in resting blood pressure between patients who have heart disease and who don't have heart disease.
Great. Okay, so, and I'm going to add just one word. You might have said this and I just didn't catch it. But for the 2-sample t-test, we specifically compare sample means instead of medians. But you could run a test to compare sample medians if you wanted to. So here, that sounds good to me. There's no difference in mean resting blood pressure among patients who do and do not have heart disease.
What would be the test you'd run for median differences? Would it be like a similar t-test type thing, or is it like called?
So to be honest, you'd probably have, there might be a test, but you would probably, the only way I can think of to do it is by running this kind of simulation that we're about to run.
Like building it out yourself.
Because I don't know what the null distribution would be off the top of my head. Probably look it up. Yeah, that's a great question. I actually don't know the answer. If you know the answer to that in the chat, then definitely let us know. Okay, and then the alternative could be one of two different things or various things. 3 different things, I guess. Let's actually look at the one, we haven't looked at a box plot for resting blood pressure. Let's do that. Oh no, we did. We did. Oh, it's here. Sorry. Okay, so we have this here. We've seen that in our mean differences that people who had heart disease had slightly higher resting blood pressure, but the medians were the same, and there's a fair amount of overlap here. So let's say our alternative hypothesis is that there is a difference in mean resting blood pressure among patients who do and don't have heart disease. Cool. Okay, so with that lined up, let's run this. So remember that the thing that we need in order to run a hypothesis test is we need to use the null hypothesis to generate what's called a null distribution. So another way of writing this null hypothesis is saying that, and I'll actually write it down. Another way of saying this is that the true mean resting blood pressure of people with heart disease minus the true mean resting blood pressure of people without heart disease equals 0. So basically the difference in the mean blood pressures for people with and without heart disease is 0, is basically what this null hypothesis is saying.
I remember writing that a lot when I took AP statistics.
Yeah.
That was like,
for sure,
classic way to start a problem.
Like the classic,
yeah.
Usually with like the Greek mu, which is.
I always loved writing out that Greek mu because it was like the first time I was using those fancy symbols.
So fancy. Yeah. So, okay. So keeping this in mind, right? Basically what we're going to want to do in order to run a hypothesis test to test this is we're going to want to say, okay, let's imagine that the true mean between these two things is 0. Let's imagine that we took random samples with the true mean being 0, the true mean difference being 0, calculate the mean difference for each of those samples and look at what that distribution looks like. That's our null distribution. And then we're going to look at the observed mean difference that we got and see where it falls in that distribution. So let's actually think this through, because I think there's different ways to simulate all these different hypothesis tests, and I feel like this one is really fun. So Jamie, do you have any ideas? And this is a tricky question, and I also will ask it of everyone in the chat. If you're coding along with us or watching along with us, feel free to answer this as well. So we have this data set, right, with information for each person. I'll reprint it, about whether or not they have heart disease and what their resting blood pressure was. Do you have any ideas, Jamie or audience, how we could simulate a situation where there's really no difference between the resting blood pressure of people with and without heart disease using this data? Kind of a hard question. I'm gonna just
so if you want to take I'm guessing you want to take random samples from the data set, but you want to make sure those random samples don't have a mean difference. Yeah, I'm not really
it's actually a really fun trick. I guess I'll give you a hint. And nobody from the chat has yet been brave enough. So we'll keep going with the suspense for a second. It has to do with this heart disease column. We're gonna do something to this heart disease column.
Oh, are you just gonna randomly assign each, could you basically just randomly assign things absent and present? So basically instead of it actually being associated correctly, it's just random.
Yeah.
And so the mean difference will go to 0.
Exactly. So part of the assumption, if there's an association here, is that whether or not someone has heart disease is gonna somehow impact what their resting blood pressure is. So each row kind of goes together, right? And the way that we're going to simulate the null hypothesis is we're going to break that. We're going to say, okay, each row doesn't go together anymore. This is just a list of resting blood pressures. And this column just tells us how many people have blood pressure and how many people don't. But we're going to we could do this without permuting this, without mixing this around by using a probability, a sampled probability, and use the probability that you do or don't have heart disease to resample this for everyone. But it's easier to just do it by basically taking this column, just the heart disease column, mixing it around randomly, and then recalculating the difference in means for that simulated data set, where the simulated data set is our original data set where we just broke any possible association between these two things.
That's really cool.
Yeah. So let's walk through how to do that kind of piece by piece. So first, let's just walk through how we would move this, how we would permute this heart disease column. So I'm gonna just write this out. So I'm gonna call this scrambled, and we're gonna take before I call it anything, we'll just do this out. So I like this numpy.random.sample function, and it takes a couple of different parameters. The first one is just the thing that we want to sample from. So we're going to sample from heart disease. Now, how many values, Jamie, do you think are we going to sample?
The same like number of data points are in the data set.
Yeah, exactly. So we're going to sample everything in this column. So I'm just going to do like len heart, which is going to be 303. And then we want replace equal to what, Jamie?
So we probably don't want to put, like when we sample a data point, we probably don't want to return it.
Yeah, I mean, so you definitely could do sampling with replacement. I believe that's called like a bootstrap. Don't quote me on that, but I think that's right. Like a bootstrapped sample. Pretty sure that's right. So you definitely could do that. But in this case, if we really just want to take this whole column and randomly rearrange it, we'll do replace equals false. So basically we're putting all of these absences and presences in a bucket, and we're randomly choosing one at a time. And then the first one we choose will be first, the second one we choose will be second, and so on. And we're going to choose all of them again, but we're just randomly, when we are randomly choosing them, we're randomly choosing the order that they're going to be in. Whoop. And clearly I did something wrong. Is this? No. Let's see what I did in my example code.
You might need to specify replace if it's not necessarily, oh, you already did specify replace.
Equals false size.
Oh, I think it's dot choice, not dot sample.
Oh, yeah. Yes. All right, guys. Okay, so there we go. We see now this has been reordered. So before the first ones were absence, presence, presence, absence, absence. Now we've got absence, presence, absence, absence, absence. So a little bit of a reordering, and this entire column has basically been reordered. So what I'm going to do is I'm going to save that as scramble. So that's my scrambled heart disease output. Whoops. For some reason, this Jupyter notebook, when I zoom in, I like can't put my cursor at the end. Okay. So the next thing we're going to do is we're going to use that scramble version to recalculate a difference in means. So we're going to say, okay, now we're going to make our simulated T-rest BPS for people with heart disease. We're going to set that equal to heart.T-rest BPS. But we're going to take just the resting blood pressures where the scrambled heart diseases are equal to presence.
So I think you have a tiny typo on the second line. I think it's BPS, not BSP.
Oh, good catch. Okay. And then I'll copy that. And we're going to do, for no heart disease, it's where our scrambled is equal to absence. And then sim mean diff is going to be the difference in means between those two. So it's going to be mean of this minus mean of this. So I see, as we're doing this, I see a question asking, is this a statistical class or Python? It's actually kind of both. It's really a stats class, but we're using Python. So if you want to also get comfortable with Python, I think this is a great way to do it, especially if what you're interested in is stats or data analysis or data science. This is a great way to also learn Python. And then And then I also see a question about using Jupyter Notebook versus another IDE. Definitely you can use any IDE that you would like. We've been using Jupyter Notebook just because it is a really nice way to save your code and output in one go. But oops, I'm not paying attention. But you can definitely copy this code over to any IDE that you're comfortable with and then run it. Also, if you have a Codecademy subscription, then you can for sure do this in our learning environment. This is actually based on a project that we currently have, and I think upcoming, hopefully soon, is a sandbox learning environment that you can use. So
I'll actually send that project to the chat so people can see it.
nice. Okay, so in this example, just to recap what we did, we scrambled absence and presence, and then given those new scrambled absences and presences, we recalculated a mean difference. And in this case, that mean difference for people with simulated or scrambled absence of heart disease versus presence of heart disease, that mean difference was negative 3.5 in this simulated sample. And if we do it again, we'll get a different number. Now it's closer to 0. Right now it's positive. So we'll get slightly different numbers each time. And what we can do is we can actually put this inside of a for loop so that we repeat it and grab these numbers each time. So I'm gonna just create a null mean diff empty list, and then repeat this 1,000 times. Unfortunately, gotta tab everything. And then what I'm going to do is in this last line, instead of printing it, I'm going to take null mean diff and append that simulated mean diff onto the end. And then so that we can take a look at it, I'm going to plot this.
Nice.
I see a question about, or someone said, I'm learning R now. I love R. If you are learning R, that makes me happy because it's just great. I've gotten so used to Python now at this point. That's also exciting for me, but yeah.
R was technically the first language I learned because I used it like a tiny bit in high school once, but then I like went to learn Python in college because that's what all my classes used. So now
yeah, it's
I don't
all
know if I know that much R left.
What your classes or what your work uses in the end. Okay, so Jamie, do you want to kind of walk through this picture? Like, what do you notice about this picture, and is it what you expected it to be?
So it's centered around 0, and it's like pretty much approximately a normal distribution. And we should expect to see it centered around 0 because of what we did in the beginning, where we tried to basically make it so that when we took samples from our data set, we scrambled the absence and presence values to make it so that it would come out as a mean difference of 0. And basically what we see right now is like just 1,000 samples of that. I think it was 1,000, right? And just like plotted. So yeah, and I think because of what we did, the way we played with the data, this is what we should see.
Yep, exactly. Yeah. So right, so it's centered at 0, exactly like Jamie said, because we simulated our data set so that the mean difference would be 0 by essentially breaking the association between those two columns. Cool. I see, quick question, how long does it take for a beginner to learn Python or any other language? I think it's a slow process. I'm still learning for sure. And as you learn more languages, you get faster at learning new ones. But for a beginner, you can definitely get off the ground pretty quickly. And then it's just a continual learning experience, to be honest, for years and years, especially because they change everything so quickly. So, okay, so this is our null distribution. And now let's actually plot our observed mean difference onto this distribution. So remember, let's actually calculate that. We'll calculate it down here. So our true observed mean difference was np.mean of heart dot t-rest BPS among heart disease equal presence. Actually, I should break this out so that we can all see it. So basically what I'm doing here is I'm saying in the actual data, what's the observed mean difference? So this is the T-rest BPS for people who have heart disease. And then we can pull out the true blood pressure of people who don't have heart disease. And then, gosh, I can't spell today. And then we can take the mean difference between them. Right? And then I didn't print it. So this we could have gotten from the table up above, but our true mean difference between these two was 5.32. So in reality, there's about a 5.32 point difference in mean resting blood pressure for people with and without heart disease. So let's plot that as a vertical line on this graph. So it's going to be plt.ax line x equals this, and color, we'll make it red. And we see that this is pretty far out to the right. We could have seen that before drawing the line too. We see that if there's really no association, that big of a mean difference is pretty unlikely. It's definitely not unheard of, but it's actually pretty unlikely, which is a little bit surprising, like given how close those two boxes were. But I guess the sample size is pretty big. And then if we want to actually calculate how many are outside of this, what we can do is we can use our same trick from before. We can take the sum of all of these values in the null distribution, and we have to turn them into a NumPy array first. So remember, all the values in this null distribution are called null mean diff. So we're going to say how many of these values are greater than the observed mean difference in our sample. And that comes out to, there are 3. And then the p-value, remember, is the proportion. So we did this 1,000 times. I guess instead of hard coding this, I can say len of this. So that's about 0.003. And then remember that this is a one-sided p-value. The two-sided p-value, we draw a line that's equally distant on the other side and also include the area to the left of that, which theoretically this thing should be symmetrical, so it should be roughly equal. So the two-sided p-value would be roughly 2 times that. So it would be roughly this times 2. And now we can actually compare this. So there's a built-in function for running there are a lot of functions that you could use for running a 2-sample t-test. I'm going to grab one that I've used before from SciPy. sorry. I see this is an example of always learning, right? I don't have this memorized of like which is the best function to use. So I gotta find it. Okay, well, here we go. So we can also run this, but instead of val achieved, we want the TREST BPS for people with heart disease, and then TREST BPS for no heart disease. Let's see. No, print p-val. And it's about 0.08. So our simulation slightly underestimated this. But if we run it again, we might get closer. Or if we run it more times, let's try that one. Yeah, so that time we got 0.008. So almost the same as what we got for the t-test that's housed within SciPy. I'm just taking a look at the chat really quickly. Are there any other questions? I see there's someone who said they didn't get a reply. Was there a question in here, or was that an earlier, or was that a different comment?
I think I'm answering his question right now because it's the most recent one. Someone also asked a question about R, and I sent them something, but I'm not sure if you have a quick answer.
Yeah, I saw someone asked about the pipe. At some point, hopefully, I would love to do a live stream on R and the pipe function because it's great. I see a question. Two sample t-tests. Does this refer to the two subsets of binary categories grouped within the data set? Absolutely. Yeah. So a two sample t-test is really, we're kind of treating these two things as our two samples. And we're thinking of them as independent samples. So there's a group of people that have heart disease, and that's one of the samples, and then a group of people that don't have heart disease. That's our other sample. And we're comparing our sample means. It's called a t-test because this distribution is theoretically a student t distribution. It's actually theoretically a normal distribution, but the student t distribution is really similar to the normal distribution. And we use it a lot of times because it's almost like a slightly squished normal distribution. It has thicker tails. And so it overestimates the p-values like slightly, which helps protect against errors. So last week we were talking about hypothesis testing and errors. And so that's why people use a t distribution, a student t distribution over a normal distribution for hypothesis testing. But yeah, we should get the same numbers. Cool. Yeah, so I see, can we test for normality with the t-test? So if you want to test whether your data is normally distributed using a hypothesis test, you would need a different hypothesis test. But if you are asking whether we could test against a normal distribution instead of a student t distribution, the answer is yes. So you could use like a two sample z test. You could basically use a z test for this as well, and you would get the same answer basically. I hope that the screen isn't too blurry. I'll try not to scroll too fast. So I wonder if that also causes it. Okay.
Sophie, I also have another random question because so this was like the variable where the mean difference was pretty small and the median difference was 0, right?
Mm-hmm.
Does that mean if we did a median, like because like the sample median difference was 0, would that mean if we like did a similar t-test style thing but with medians like we were describing earlier, would we get a much different result from it?
Probably, yeah. Do you want to try it? So let's just say we wanted to get a null distribution for the medians. I'm just going to copy this down. So we're going to do exactly the same thing, except we're just going to calculate the median difference here instead of the mean. And then append that. And then we'll plot a histogram of this and show it really fast. And we'll see. Whoop. Yeah, so basically it looks like this distribution we get is really, we can add some more. Here, I'm gonna reprint this with, is it bins? 50?
Oh, wow.
Wow. Yeah, so basically what's happening is that the median in the simulated null distribution is almost always 0. It's very rarely these other numbers. So it's, I guess, hard to calculate a p-value here based off of this simulation.
Yeah.
I don't know actually what this distribution should look like. Super interesting.
Huh.
It's just a very condensed distribution. Like 0 is by far the most common. Yeah, that's interesting. So yeah, so the p-value, I mean, our observed median difference was 0. So the p-value would be like 100%.
Yeah.
Right? The p-value would never be that small. Yeah.
Yeah. Huh. It's like so weird that the mean and median would have like such a different like evaluation of the test.
Yeah, for sure.
Huh.
And like, I think the reason why people use the mean generally is that the central limit theorem applies, which is to say that because we have the central limit theorem, and this is getting into the weeds of things, but right, the expectation of a difference or of two random variables added together is just the sum of the expectation. So basically like the distribution, I guess it doesn't matter so much expectation, but basically if you have two normal distributions, their sum is also normal. So, or their difference. So basically like this is normally distributed, and we know that it's normally distributed, or student t distributed if we want to be conservative. So it's very easy to run this test. Cool. So we are also running pretty low on time, but I think it's worthwhile to just show, since we spent most of the time on the t-test anyway. Let's see, can I? Pull this over. If you look in the final code for this week, you'll see that we did this for a few other variables. And you'll see, for example, that the p-value for resting blood pressure was 0.008. For cholesterol, I think it was even higher, 0.139. And if you look at, I think I did the simulations out for a couple of them. So this was the simulation that we just did. This was a different simulation of basically the same thing. I again got, I think 0.008. But if you were to simulate out with something where there's a more clear association. So I think I did with an example with the chi-square test out here, which is like, this is my null distribution and this was my observed value. Then this is where you get like those super small p-values, like 0.0000017 or something was one of them. Cool. All right, what do you think, Jamie? I think we're gonna kind of run out of time. So I'm just gonna run through really quickly some of the other tests that you can run and things that people might want to look into if they're interested in learning more about this.
Yeah,
so
that's a good idea.
if you take this course on Codecademy, you're going to see a few other different types of hypothesis tests. So you'll see something about the ANOVA hypothesis test and Tukey's range test, which are useful when, in our example before, right, we had a binary variable. So again, back to the 2 sample t-test, right, we have either heart disease or no heart disease. But what if we are instead interested in how that thal achieved, or whatever the heart rate that you achieve, is related to what kind of chest pain you have? And there are actually 4 different kinds of chest pain, not just 2 categories. So if you want a hypothesis test to understand whether there are differences between any of the pairs of these 2 categories, right? So there's a bunch of different pairings that you could make. Then you can run an ANOVA test, and you can then follow it up with Tukey's range test, which will tell you where those differences lie. So in this example, here's an example of a Tukey's range test looking at the association between type of chest pain and thal achieved. And when we look at this output, we see that there are significant differences between the asymptomatic group and every other group with respect to chest pain, but there's no significant differences between the other groups. So the true, right, means that the p-value was small enough at a level of 0.05 to reject the null hypothesis and say that those 2 groups are statistically significantly different. And then we can see that in this picture, right, where the asymptomatic group has a lower thal achieved than all of the other groups, but the other groups seem pretty similar. And then the other hypothesis test that's included in here is the chi-square test, which is used for looking at an association between 2 categorical variables. So in this case, for example, people who have and don't have heart disease and different types of chest pain. So is there an association between whether someone has heart disease and what kind of chest pain they have? And we can run that hypothesis test using a chi-square test. And if you are interested, I have included some questions or some examples at the end in the final code that's available on GitHub, where I simulate a chi-square test. So if you're interested in learning how to simulate a chi-square test, you can look there. Essentially, all it is you say, okay, what proportion of people have heart disease? I'm going to randomly assign whether or not someone has heart disease based on that proportion. And then I'm going to randomly assign whether or not someone, or what kind of chest pain someone has. I'm going to randomly assign them separately. We can even do exactly what we did before, which is like randomly permute this row or this column of the data set and randomly permute this column of the data set, recalculate the chi-square statistic every single time, and look at that null distribution. So with that, I think we have 1 minute left. I'm looking at the chat to see if there's anything else I can address. Sorry.
Sophie, I did mention, because someone's asking questions about like R and statistics-based questions.
Yeah.
I did direct them to like the forums and mention that you like answering questions about R and statistics.
Yes, definitely. If you post in the forums, you can definitely tag me. I also keep an eye on the forum questions, but I think my tag is SophSummer3. I will double check that. But yeah, definitely post in the forums. I check them and I love talking about stuff. I don't know off the top of my head what the Shapiro test is. I'm seeing this question about t-test versus Shapiro. Let's look it up really fast. Oh, for normality. So, Shapiro-Wilks test. Right, so Shapiro-Wilks test is for testing whether a distribution is statistically significantly different from normal. So it's actually like, I've seen this used, now that I'm seeing this, I've seen this used to check assumptions for a model. So for example, if you are going to write up or try to design a predictive model in order to predict resting blood pressure based off of other characteristics, one of the assumptions is that resting blood pressure has to be normally distributed. And so if we look at it, test BPS, and show, it may or may not look normally distributed. This doesn't really look normally distributed. It looks kind of skewed. And so then if you wanted to test, is this significantly different from what a normal distribution would look like, you could use the Shapiro-Wilks test. The t-test is specifically testing for mean differences between two groups. So looking at an association between a quantitative outcome or a quantitative variable and a binary categorical variable. Okay, well, Ed, you can go back and hear my answer to your question, hopefully. Cool. So hopefully we got through all those questions. If you have more, I love hearing from you. Post on the videos in YouTube, post in the forums on Codecademy, talk to me, tell me that you like these, tell me that you hate them, tell me what we can do better. These are really, we hope that learners are getting something out of this and that we can have this kind of little community. I know both Jamie and I know the same is true for Alex, we all love kind of having connections to everybody that is learning on our platform. And we also are constantly learning ourselves. So this is really fun for us to get to, even though we're all kind of locked away in our houses, get to interact with you all and hopefully learn from each other. So cool. Well, with that, I hope everyone has a great rest of their Tuesday.
Thank you for letting me join with you, Sophie.
Thank you for joining. Thank you so much, Al. Or thank you so much, Jamie.